Right, good afternoon. Today we've got paper 2 from last year's Edexcel stuff from A-Level Maths. Today's paper 1, so this should be posted by the time you get home from doing that one. So good luck on that. Let's have a look at this stuff. So factorise completely, 2x cubed minus 24x squared plus 40x. We can take an x out straight away. 2x squared minus 24x plus 40. Need to factorise now. Numbers at times to make 8 and add up to make 24. But actually, we've got a 2 there, so let's take a 2 out as well. 2x, x squared minus 12x plus a 20. So numbers that times to make 20, add up to make 12, or take away to make 12. So looking at that, we have a 10 and a 2. So we have minus 10, minus 2. Hopefully nothing too bad on that one. Lovely jubbly. Number 2 then, same sort of stuff, but integrating. So when it's x to the 4, raise it up to x to the 5, divide by a 5. 6 to the half, raise it up to 3 over 2. And that 6 will times it by 2/3. And minus 3 x. And this 6, not 2/3 of 6, what's that give us? That is 4 altogether. Can also do that in one go if you like. No harm in doing it in 2. That all looks good for me. Very nice. 4 marks. Very nice 4 marks there. One thing to remember though, plus C every time. No limits, always a plus C. Number 3 then. 3 to the power of x is 7 to the power of y. So we want x over y. So to get the powers down into the kind of base level, we're going to take logs of both sides. You could do any base here, 3, 7, or e would be nice. I'm going to do just e because that's what I normally do. So we'll have x log 3 is equal to y log 7. We want x over y, so we'll divide by the y, divide by the log 3. We've got log 7 over log 3. You could rewrite this as log base 3 of 7. Both would be completely fine. Both will get you all the marks here. Lovely jubbly. Looks good to me. Number 4 is somewhere. There it is. So we've got this thing, whatever this is, big triangle. Shape, blah, 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 is a triangle and a sector. We've got some numbers that are on the graph already. This is also 8. Show that this angle is 0.394 radians. So ABC. What we have then is a triangle. Where do we have anything else about it? No, but we've got a triangle. So we're just going to use cosine rule. I don't know if there's a short way to do it, but no, cosine rule is what it's going to be. So a squared, 6.4 squared is equal to b squared, 13 squared, plus 8 squared. Take away 2 times a, which is 8, times b, which is 13, times sine of, times cos, for the cosine rule, of the angle. I'll call it theta. And now then, we want to rearrange this for theta. So what do we get? 6.4 squared. Take away 13 squared. Add or take away 8 squared. All over negative 2 times 8 times 13. That should be cos theta. So we can just do inverse cos of that to work out what theta is going to be. Let me move that over a little bit. And let's work that in the calculator. Inverse cos 6.4 squared minus 13 squared minus 8 squared over minus 2 times 8 times 13. And we get a number of something in degrees, which is not useful. We go to radians, we do it again, and we get a number of 0.394, which is exactly what they wanted. So that's always a good sign. Part B then, find the area of that shaded region, give it in 3 sig figs. So the area of the shaded region, we've got a triangle and we've got a sector. So the area of that region, the area of R, is going to equal to the area of the triangle. So the triangle BAD. Take away the area of the sector, which is ABC. I don't know if it matters if you write like ABC, CBA, or ACB, whatever. I don't think it makes a huge difference. Doesn't make a difference. Don't think so anyway. Not for A level. So the area of that triangle, we're going to have half AB sine C. So half of A, 8 times 13 times sine of theta. And we're going to take away the sector. So the sector will be r squared, so 8 squared, times by a half, times by the theta. So all together, what have we got? We can take a half and an 8 out. And then it's going to be 13 sine theta minus 8 theta. Doing that then, what do we get? So 4 at the front, 13 sine of the thing I've just found, take away 8 times the thing I just found, gives me an answer of 7.36 when we round it. It might be a case when you do this. So we got 7.36. I've used not 0.394, but the actual answer that was appeared from here. So it may well be that you're like 7.35 or 7.37, very close to it. You'll get the marks either way. It should be like they accept this or they accept the other one. Both are fine. So that looks good to me. Let's go on to number 4. Number 5. Not very good with the numbers, me. So what have we got? We've got x, we've got a y. P has x coordinate minus 3. Find the y coordinate. So let's set this equal to minus 3. T minus 1 over 2 equals minus 3. Rearrange this. 2 times minus 3 is minus 6. Add a 1. T is minus 5. When we take that t, plug it into the y, what we're going to get? Minus 5 plus 2 minus 3. So y is going to be 5 times 3 to the 4. 81 times 5 is 405. I'll double check that. 81 times 5, 405. That looks good to me. Part B, what have we got? Find a Cartesian equation for this. Okay, so we've already kind of got this one. Let's rearrange that for t. So 2x plus 1, that will be t. We actually want t plus 2 though, so let's add add 2 to that. So t plus 2 is 2x plus 3. So that whole thing is 2x plus 3. So what we have, y is 5 lots of 2x plus 3 all to the power of 4. Hence or otherwise, find the gradient of c at p. So let's differentiate that. dy dx is going to be the 5 from the front, the 4 from the power, the 2 from inside the brackets, and then a 2 plus 3 to the power of 3. And we want this at the point P. P was at the same point? Yeah, minus 3. What was the t value? Minus 5. So again, minus 5. If we double that, we get minus 10. No, this is x, that's not t. So yeah, very easy thing to slip up on. What was the x value? X is minus 3. Okay, so minus 6 plus a 3, that's a minus 3 still. So we're going to have 40 times by 3 cubed, minus 3 cubed. So 40 times 27 gives us 1080. So negative 1080. All looks good to me. Yep, looks good. Let's keep going. Did I miss a question? No. Number 6 then. Given that x is small and in radians, use the small angle approximations for cos theta to show that this is true. Okay, so in general, cos theta is roughly 1 minus theta squared over 2. So now we've got that squared down here. So what we're going to have is the 1 from that 1. Take away the whole thing squared. So 1 minus something squared. That something is 2x. All over 2. And that whole thing squared. So looking inside the brackets for a second. Open this out, 4x squared. Half of that, 2x squared. So we got 1 minus 2x squared. All squared. And now we're going to expand that bracket out. So still the 1 at the front. We're going to have a 1 minus 4x squared plus 4x to the 4. And those two 1s will cancel out. What we're left with, 4x squared, take away 4x to the 4, which we can factorize out if we want to, but that's actually enough for the answer. I will factorize though, just you never know. So 4x squared there, 1 minus x squared on that one. That all looks good to me. Given that x is small and in radians, use the answers by A and small angle approximations for tan and sine to show that this is true. Okay, so the top row, the numerator, is just what we did. No difference there at all. The bottom, sine and tan are just themselves, and whatever you have in there is the approximation. So this approximation is going to be the thing we just found, the 4x squared, x minus 1 squared, over x on 3 times x on 2. If we look at the powers of x squared there, these are x squared, so they all cancel with each other. And then we've got a 6, like 1 over 6 on the bottom, so we can times by a 6 top and bottom to have a 24 up there, and then a 1 minus x squared, and that is all we have left over. So it's A and B are both well. A is 24, B is minus 24. In that form, I will just rewrite it. 24 minus 24x squared. That's good. Given that x is very small, so what I'm taking for that, we want an approximate value for this thing. Very small. Generally, you're going to write that as like x is very much less than 1. So in that case, I'm thinking it's basically 0. So effectively, we can say that x to the power of n is roughly 0 for all n bigger than 1. Like if you ever have a number that's like, if you've got power bigger than 1, you're squaring it, cubing it, even like 1.5, something like that. You're making the number smaller if it's less than 1. And what we're saying is it's so small already, when we do powers of it, it's just gone away. Do you know what I mean? If I have something that's 1 over 1,000 and I square it, I've got 1 over 1,000,000. Is that making a difference? A little bit, but not really at the end of the day. So we've got an approximate value. X squared is going to be 0. So this thing should be just roughly 24. And it basically means that if we could plug in 0, we can't do, but if we could plug in 0, we would get 24. That all looks good to me. Let's keep going to number 7. So, one of these things. All right, we've got big thing on the top, little things on the bottom. So yeah, they've already given us this stuff, which is good. So let's take this and write this as if we have one common denominator of these two brackets times together. So this term is times by both. So we have ax, x plus 1, x minus 3. The b as well, same thing. B lots of x plus 1 and x minus 3. The c already has an x plus 1, so it only needs x minus 3. And then similarly, the d already has the x minus 3, so it only needs an x plus 1. Try and squeeze this in. So yeah, only an x plus 1 over there. That's good. This you could write under, like, have the bottom with both bits, but this effectively is the top row, so it's just equal to these bits. And actually, triple equals. Always the same for every single value of x. So to do this then, there's a few ways you can do it. Either you can start plugging in like 3 and minus 1. First off though, I'm going to plug in nothing and I'm going to think about the coefficients of the powers. So if we look at x cubed, on the left we have 3. On the right, where do they come from? For all of these terms, this is a linear, this is a linear, this is a quadratic. They do not have an x cubed. The only one comes from here. How many do we get? A of them. So A is 3. I'm doing a very similar thing now, looking at the squares. How many on the left? Minus 8. How many do I get to these places? So we can have a look in here and think, okay, what powers of just normal x do I get in there? I would get 1 minus 3 minus 2. So there's minus 2 a's, minus 6. Plus, I get 1 from the b. So adding that 6 over, b is going to equal to minus 2. That looks good to me. You can do this continuing. You can keep going with like the x1s and x0s. Gets a bit tricky when you've got so many going on. You end up with simultaneous equations. So now it's going to be a case of just we'll plug in the values and see what's going on. So if we go and plug in the value of 3, what are we going to get? So this is why it's tedious. We need to plug 3 into that now and see what that's going to be. So 3 to the power of 4, take away 8 times 9, take away 6 times 3, take away 11. We have a number of minus 20 on the left. When you put in the 3's, this is gone, this is gone, this is gone. 3 plus 1 is a 4. So 4d is minus 20. So d is minus 5. And the last one, we will plug in the value of minus 1. Minus 1 is quite nice to do with these. You're just going to alternate. So this here, we're going to have a negative because it's the minus 1. So minus 3. Then we want to match what they gave us. So minus 8. Then we want to do the difference what they gave us, plus 6. Then match what they gave us, 11. So doing that, we have minus 11, minus 22, minus 16. And on the right hand side, we put in a minus 1. That's gone, that's gone, that's gone. We've only got this. So that's minus 4 lots of c. So c is going to be equal to 4. So that all seems right. The numbers are not quite nice. We haven't got any horrible fractions flying around. Everything seems pretty good. So A3, B minus 2, C is 4, and D is minus 5. Yep, all looks good to me. Let's keep going. It's quite tedious, isn't it? 4 marks for that. It's quite long-winded. compared to what it could be. There's probably maybe quicker ways, but this seems easiest to do. So we've got some quartic. Figure 2 shows a sketch, blah, blah, has a local maximum at minus a quarter. So that's going to be this point, yeah, this thing here. So that is minus a quarter. Show that A is, minus 1 and 4. So what we need to do, two ways. You can either plug it in and then differentiate it, set equal to 0, so that's a solution. Or we can like differentiate it, set equal to 0, plug in minus a quarter, and then solve for A. I'm going to do that way around. So yeah, if we differentiate, what are we going to get? So f dash of x will be 4x cubed plus x squared. Take away 16x plus an a. And now we know that when we plug in the value of minus a quarter, that should equal 0. So let's do that. We're going to have a quarter cubed times by 4. So it's going to be 1 on 16, but negative. So negative 1 on 16. This thing is squaring that thing, so that's positive 1 on 16. This thing is negative 16 times negative 4, so that's going to be positive 4, and then positive 9. Positive a, sorry. It's an a, and yeah. My a's are not very good at looking like a's. I might just do a capital. A equals 0, so therefore a needs to be minus 4. Lovely jubbly. That's one thing to note. If your handwriting, if you have bits that look the same, like my 9s and my a's look very similar, don't mess that up in the exam. Do something different. Just write down somewhere very easily, like equals a, so they know that you're referring to that. I imagine it would be fine if you used a instead of lowercase a. I think it would be okay, but you don't want to risk it, so just write like a equals a. That should all be okay. That looks good. Find the y coordinate. We just want to plug this value back in. So we had a as minus 4. Let's plug in a value of minus a quarter into that then. So minus a quarter on there. It's not going to be so nice. It's going to be not very nice at all. So minus a quarter. 1 on 256. Yeah, 1 on 256. 4 cubed. 64. So we've got 3 times that. 192. Minus 8 times, well, 8 over 16 is a half. And then we've got the a, which was minus 4 times this, so they just cancel out and make a positive 1. And then the positive 17 over 3. Let's add those all up. 1 over 256 plus 1 on 192 minus 0.5 plus a half plus 17 on 3. I get a number of negative 3961 on 768. Shouldn't be negative, should it? Definitely shouldn't be negative. So something's gone wrong there slightly. What's gone wrong there? Negative a quarter. This should be a negative number. No, that should be a positive number. This one should be negative. Yeah, where we had the cube and it's a negative thing, that should have been a negative. So this one should be negative. Negative a half, was that fine? The square gets rid of the positive, makes it a negative. Yep, that looks good. Negative a quarter times by negative 4 is positive 1, and that was positive. So yeah, let's just swap this one over to a negative. Does that change anything? It still keeps us negative, so something's gone wrong here. So let's have a little think. Let's just try my numbers again. So I did minus a quarter, minus 1 on 4 to the power of 4, 1 on 256, so that's good. Then we've got a third of negative 4, no, negative a quarter, all cubed, negative 192, that's good. Negative 8 times negative 0.25 squared, negative a quarter. Negative 4 times by negative 0.25 is 1. And 17 on 3 is 17 on 3. Have I typed it in wrong? Don't think so. Local maximus definitely needs to be positive. Did I I'm not even differentiating, it's just plugging it in. And we did get the value of a quarter. What have I done wrong? What have I done wrong here? We know it is wrong, don't we? We know it is definitely wrong. Let's maybe try and do it all in one go. So we'll have minus 0.25. And I'm just going to do answer to the power of 4 plus 1 on 3 times by answer cubed minus 8 minus 8 answer squared. A itself was minus 4, so minus 4 answer, and then plus 17 on 3. Now I do get a positive answer. I get 4735 on 768. So that looks better. 768 is a nice sign. I'm going to trust that one. I will trust that one. I will double check at the end to see if that's all okay. But that does seem better. I don't know what went wrong here. Yeah, ignore. I might just cut that out, but we'll see. Yeah, not too sure. So that's that bit done. Next one then. F of x equals k. Okay, as a constant has 4 distinct solutions. Use algebra to all stages of work and find the range of values of k. Okay. So what we can do is let's just draw a line like y equals k, some horizontal line. At this point, we hit it twice. Then we hit it 3 times. Then 4, 4, 4, 4, 4, 3. Back to 2 again, back to 2, and then back to 1. So we want that range here from here up to this bit to be where our kind of min max k is. So this is going to be a maximum k. And if I can move it, this one will be our minimum k. This is y equals k max. And here y equals k min. This thing we just found, this is k max. This is k max because it is just the height of this turning point. So we need to find the height of this turning point, the minimum down there. We had f dash of x, and the a that we found was minus 4. So we have our equation, which we could just rewrite. So f dash of x is 4x cubed plus x squared minus 16x, and then minus 4 for that a. We want to factorize this. Well, we want to solve it equal to 0. So effectively factorize it. We knew one solution is at minus a quarter. So one bracket here is 4x plus 1. Where does this 4x cubed come from? 4x times something. X squared must be that something. Same question about the minus 4. It must come from 1 times minus 4. And then if we look at how many we have, I have so many x squareds there. I need to have none of them because I've already got one. I've made one there. So these two must combine together to make 0. 4 times what is 0? 0 x's. So this is 4x plus 1. And then x squared minus 4 is x minus 2, x plus 2. So what we must have is that this value is obviously a negative x, so it's negative 2 something. So let's take our negative 2, plug it back into here. I'm going to do the second version, not faff around with that first one again. The second one, if I just press 2, if I press negative 2, and then I go up, press equal again, I get a value of minus 5. That seems quite nice. So what we're going to have is we need to be above minus 5 and below this value we had for k max. We can be equal to either because they're the points when it's exactly 3. So it needs to be between those two. So minus 5 is less than k, which is less than that number of 473 over 768. Yeah, that looks good. Numbers seem right. That's negative. That is positive still. This one I will double check that's right, but it seems good. Basically, if it's correct, you won't see me say anything. Do you know what I mean? So if it just goes to question 9 now, it's correct. If I say something, it's incorrect. So question 9, what have we got? A new type of car is released for sale. The total number of this type of car sold, n, in a particular region, t months after the cars were released for sale, is multiplied by this equation. So one thing to note about the way they phrased that, total number of types of cars sold, t months after the cars were released, it's not how many we sold in the tth month. It's how many we've sold cumulatively after t months have passed. So not how many we sold in month number 3 or month number 4, but how many we sold in the first 3 months or the first 4 months. You can see that if you look at the graph of this equation, it comes up and then settles at 5,000. So the idea being that like this is counting how many we've sold each month, like in total, how much we've sold now. And we're going to settle at some number. We sold 0 to start with. We sold so much after month 1, 2, 3. But how many we're actually selling per month is just these heights. So we are selling less every month, effectively. So total number of cars sold in the first 3 months, we're just going to plug in 3. So we've got, I'm just going to rewrite this as well. This is 5,000 lots of 1 minus e to the minus 3t on 40. Yeah, 3t on 40. So doing that, plug in the value for 3. We're going to have 5,000 lots of 1 minus e to the minus 9 on 40. Let's see what number that gives me. 5,000, 1 minus, where's my e? E to the power of negative 9 on 40. We get 1,007. If you round it down from the, 1,007.42. So yeah, 1,007. Given that n is 3,000 when t is t, find t. Okay. So just in reverse then, this thing now equals to 3,000. So it's effectively like 3/5 is equal to the bracket of the 1 minus e to the minus 3t on 40. If I add this over, take that away, I've got my e to the minus 3t on 40 is equal to 2/5. So taking logs, minus 3t on 40 is the log of 2/5. And then we'll divide by 3t on 40. So negative 3 on 40. So t is going to be negative 4 on 3, so 40 on 3, log of 2/5. And I can use a negative to flip that over. 40 on 3, log 5 over 2. What number is that? 40 on 3, log 5 over 2. I get that it is 12. How many decimal? 3 sig figs, 12.2. So we've got that one and that one. Looks good to me. Always make sure it makes sense as well. I mean, 12 months, they sold 1,000 in the first 3 months, and then they've sold another 2 grand in the next like 9 months. Yeah, that kind of makes sense. So after a campaign, the total number of cars sold is expected to rise and have an upper limit of 6.5 grand. Use information, just one refinement. Well, the 5 grand, like it is, they're capping out 5 grand. The way to view it, does it have it down here? No, just adjust it, yeah. So this E is always positive, yeah. So 5,000 E's always positive too. If you take that negative, they're always negative. So this thing is always negative. So you're always taking something away from 5,000. So at no point could you be bigger than 5,000. That's what it's saying there. We want to change that now to be 6,500. So all we're going to do is like the 5,000s are now 6,000. 6,500. So it's basically that 5,000. If you think this way round, this is the theoretical maximum limit you could ever sell. So we just want to change that number to 6.5 grand. All looks good. Let's keep going. What have we got? So water in a large container. The tap at the bottom, T hours. So the T hours, we've got time. This is rates of change. Connected rates of change. It's not just like the connected changes thing where you like talking about the container itself. Here we're filling the container. So we need to show that this thing's true. So we want dv dt. What information does it tell me? What is flowing into the container at 0.45 per hour? So we're going to add that on. What is leaving at 0.3 V per hour? So to take away 0.3 V, I'm going to factorize a 0.3 out straight away. So 3/10 come out. I've got a 3 there. Take away a, no, tell a light. I'm going to take away a 0.15 out. So over 3/20ths, I've got a 3 there. Take away a 2V. And I'm actually going to put that 3 back in. Look at the numbers here, 9 and 6. This is a 20. Yeah, we're just done, aren't we? So 20 dV dt is equal to 9 minus 6V. Lovely jubbly. It's always good when it's correct. Given that tap was opened, there was 0.25 meters of water. Solve the differential equation to show that this is true. Okie dokie. So, first thing to do is going to integrate, isn't it? So we have v's on the right hand side, but it's a differential equation. So our dv is on top. So we're going to have dv over 9 minus 6v is equal to 20 dt. Integrate on both sides. This is that log thing. So we need the top to say minus 6 because it's the derivative of the thing on the bottom. So to get that to happen, we must divide by negative 6 as well. Left-hand side then is going to be negative 1 on 6 of the log of 9 minus 6v. And this right-hand side is just 20t plus a c. One thing to note, we have this minus 6 over here, so I am going to put that over there in a second. We could have immediately just made this minus 120 and doing that. But we have this c here, and you could think of times that there, make a minus 6c. It doesn't really matter too much, because c is just going to be a constant. But to make it be a bit nicer to deal with, I'm going to call this c instead, c over 6. Because it's still just some constant in it. Doesn't matter if I call it c, doesn't matter what you call it, as long as it's something that isn't t and isn't v, basically. So doing that, let's times it by 6, times it by a negative as well. So we've got the log of 9 minus 6v. Actually, do we want to times it by negative? Nah, we'll leave it as it is. No, we will times it as a negative. It's going to be negative 120t minus c. Logs of both sides, 9 minus 6v is equal to e to the minus 120t minus c. And now we're going to separate that out. This is the same as having e to the minus c, e to the minus 120t. And then that e to the c we're just going to call a. Hence why we weren't really too fussed about what we called c, because c is just going to go eventually. Do you know what I mean? We don't need it. What we really want is e to the c. You can, if you want, call this log c. It's not a bad way to do it as well. So now let's rearrange for the v. If we add the v over, we need to take that away and then divide by 6. So it's 9 minus this stuff, a e to the minus 120t, is going to equal to v. Often you'll see that we have two unknowns in here, but we didn't in this case. We just had the actual, like, there was no k. I mean, it wasn't like we're losing it at so many, like, we didn't know how much we were losing it. So this is good. We have our thing of when the tap is opened, there's 0.25. So that tells us that our volume of like TV, we have a coordinate of 0 and a quarter. So let me plug all those in. 1/4 is equal to, if we make t 0, this whole thing is going to be e to the 0, which is just 1. So it's 9 minus a. So what we have is a is going to be 9 minus a quarter. So 35 on 4, I think. Looks good to me. That doesn't seem good to me, actually. Something feels wrong. Yeah, something feels wrong, but I'm not too sure. The numbers seem too big. I didn't divide by a 6. So in these, like, if something feels wrong, it probably is wrong. So let's do that little step again. We're going to add the 6 over, the 6v over, take that away. So we'll have the 9 minus a e to the minus 120t over 6 is v. Yeah, that's better. So now v being a quarter is equal to 9, again, minus a over 6. Yeah, so, okay, that being a 9 still. We're going to have 3 over 2 is equal to 9 minus a. So a is equal to 9 minus 1.5. So 7.5, 15 on 2. That does seem a little bit better than it was before, but still something there is not feeling right. Did we do one thing wrong? Times by 6, times by 6. 20t, 120. That's good. Seems okay. Doesn't seem like we've done anything wrong, I don't think. No, it doesn't seem like we've done anything wrong. So that will be okay, I reckon. But I will double check it again. So if you see, like, if we go to the next question, then we'll be fine. So given that the capacity of the container is 2, the tap remains open, water flows into the tank at the same rate, will the tank ever become full? So what we can think about is, sorry, I had to find it 5 minutes then. Yeah, determine if it's going to be full. So we have our equation. Let's rewrite this a little bit neater. So we've got it over 6. 9 over 6 is 3 over 2. And then the a over 6, so that's 15 over 2. Take a 3 off, make it 5 over 2. But then you've got us 2 there still, so 5 over 4 of e to the minus 120t. And now then, what we have is that this has a max. It's the same thing as last time. This whole thing is positive. So, like, including that bit, your whole thing is negative. So you're always taking something away from 3 over 2. The maximum height was 2. So we're never going to get to 3 over 2. So we can say straight away, like, V is less than 3 over 2, which is less than 2. So therefore, we do not fill. It never is full. Never full. You can kind of see it from up here as well. So if we were to plug in, like solve this for 0, think when is the change of the volume 0? We would get 3 over 2 for the V. So what if you ever get to 3 over 2 full, it wouldn't change from there. So as you come from below, you can't go through that value because that's a maximum. Do you mean you get stuck there? Or you're above it and you just would be, you get to that point, that would be minimum and it's back up again. But we can see here that we are beneath it. So because we're beneath it, we're stuck beneath it forever. So this is looking good. This is telling me, like, I feel like that means that this is correct because that's the right number to be like the solution there. So I feel that's right. So same thing, if this is correct, question 10 appears, question 11 appears next. If it's wrong, you'll see me correct it. So number 11. Company trying to determine the most profitable selling price for a new toy. Given that if they sell it at £30, they sell 1,500 of them. If they sell it at 50 quid, they sell 300 of them. So using a linear model, with y being expected number of toys sold and x being pounds, find an equation. So linear model, we want to find the gradient. They've sold, y being toys sold, so they sell 1,200 less for every £20 more. The gradient is minus 1,200 over 20. So that's going to be minus 600. Yep, don't know why I was so did not trust my math then. So yeah, we have that, and we can then kind of figure out backwards what it's going to be. So minus 600x plus a c. So c itself should be y plus 600x. So let's do the top one. 1,500 plus 600 times 30. So plus a 1,800. This all seems too big. Why does it seem too big? Yeah, it is. It's 60 in it. That's why. Seeing this seems way too big. Everything's massive. Always trust your gut. If something feels kind of wrong, do you know what I mean? Something is probably wrong somewhere. Let's trust this bit again. So it's y, which is the 1,500, plus 60 times 20. So 6 times 20, 120, plus 1,200. Sorry, 6 times 30. 6 times 30 is plus 1,800. So 3,300 for that one. So altogether, y is minus 60x plus 3,300. Looks good to me. Given that cost of making each toy is £10, they come as additional cost of £8,000 per year. Show that according to the model, the yearly profit in thousands is given by this thing. So profit, how are we making profit? Well, you need to sell things. How many things are we selling? That was y, wasn't it? Y being the expected number of toys sold. So if we sell y, how much money do we actually bring in? Well, if we sold each one for £10, it would be 10y. But we're selling each one for x pound. So it's actually xy is how much revenue we're going to make. The cost of each toy is £10. We sold y of them. So we take away 10y. And then we also always have to spend £8,000 a year. So we need to do 8,000. Either do this all in terms of like thousands now, or all in terms of just normal money, like in terms of pounds. Let's double check everything's fine. This was doing it in just normal numbers, wasn't it? Yeah, this is just normal numbers. This is normal numbers as well. So let's do normal numbers for a second, and at the end we'll cancel down. You can think of a saying like this is actually thousands of pounds. So let's have a look. X times y. Y was this thing. So let's do x times that. So we'll have minus 60 x squared. That's a good sign with that coming up. Plus 3,300x minus 10y. So minus 10 lots of this. So it's going to be plus 600x minus 33,000. And then we've also got the minus 8,000 as well. Let's collect some of these bits. Still minus 60x squared. How many x's? I've got 3,900 x's. And then I've got minus 41,000 of that bit. And if I divide by the 1,000 on both sides, p is going to be exactly what they wanted, 0.06 negative of that x squared plus 3.9x minus 41. Looks good to me. Given the company wishes to make a profit on the sale of the toys, find the range of possible selling prices of the toy. So to make a profit, that means p is positive. So we want to solve this equation equal to 0 and find when it's valid. I think you guys have calculators that can do that on it. So I will choose a calculator as well on like Wolfram Alpha. So doing that, we get minus 0.06 x squared plus 3.9x minus 41. What numbers do we get? So we say it's equal to 0 to start with. So equal to 0 tells us that our x, the number of toys we're going to sell. Was x the toys we're selling? No, x is the price and x is the price. What numbers do we get? We get 13.18 up to 51.81. So therefore, we need to sell them between that number. So more than 13 quid or 13 quid 18 and less than £51.81. All looks good to me. The maximum selling price is just the average of these two numbers. So whatever that ends up being, 13.18. My calculator's turned on. 13.18 plus 51.81 divided by 2, 32.5. Imagine I've rounded both of these, and these actually like add up to a whole one, don't they? If you don't need to do the first part, you can just do like the quadratic formula of that square root. It's this number. It's where the turning point be. You could also just differentiate as well. Any way to do it. If you know the roots, it's always the middle. Quadratics are completely symmetrical. So if you know that, yeah, if you've got two y values, if you've got two of any value, these could either be both y's, both x's, so I mean both 7s, both 10s, would be fine. The middle of them will still be the root. In 1 year, the company sold a toy for 35 and made 21 grand profit. Evaluate the suitability of the model. So as we plug in the value of 35, what do we get? So doing that, we'll have the 0.06 negative 0.06 answer squared plus 3.9 answer minus 41. We get 22. That refers to 22,000. So what we can say is that the difference, how wrong it was, so the wrongness was 250 quid, yeah? So what percentage is that? So 250 quid out of the 21,750 that they actually made. So 250 over 21,750. If we times that by 100 to get a percent, what we have is that they are off by 1.15%. That's a pretty good error. That's, if I predicted anything between 1.1% accuracy, I'd be quite happy with that. So I'm going to say, yeah, suitable. Is that the word you used? Yeah. Is it suitable? I'd say yes. This is low percentage error. Lovely. I think you could do absolute error. I think if you want to say like the close, it would be fine. However you want to do it, I think it should be okay. It's only 2 marks. You get 1 just for working out the number, or working out like how much you actually made or the wrongness, and then you're just saying like, is it good or not? But you can kind of think, yeah, if I predicted 21 and 3/4 and I got 22, or vice versa, I'm happy with that. I mean, that's good enough. Always usually like, yeah, there's no kind of barrier to be like, when is it not suitable anymore? It's always up to you, subjectivity. So as long as you explain yourself and say why on yes or no, that could be a reason, then you're fine doing. Let's keep going. We got this modular stuff, 4 lots of x minus 3 minus 5. Given that a is a constant and mod of a is 1, find the possible values of f of a. Well, what this tells us, a is plus or minus 1. So we need to do f of plus or minus 1. So if we look at that, if it's plus 1, 1 minus 3 minus 2, modular that, 2, times by 4, 8, take away 5, 3. If it's minus 1, take away minus 3, well, take away 3, minus 4, modular that's 4, times by 4, 16, take away 1, take away 5, sorry, is 11. Looks good. G is defined by this. Find the range of values of GF. Well, let's work it out. We've got x minus 3 in the modulus. That must be positive. Same if you times it by 4. Makes no difference. If we now take away 5, we have that this thing is bigger than minus 5. So that thing that we just built is f. So we know f is bigger than minus 5. So when we go and look at this now, we want to put f into g. So really want to think about the fact that like our f is bigger than minus 2. That is the x here. So bigger than minus 5. Let's times it by 2 then. So 2f bigger than minus 10. and we'll add 17. 2f plus 17 is going to be bigger than 7. So therefore that is g. G is bigger than 7. You can take upper end as well, but we had no upper end on the f, do you know what I mean? So we also have no upper end on the g. It might be you have no lower end, do you know what I mean? It could be that you just have, you're missing one end. One end doesn't exist. Doesn't always happen, but in this case it did. This is just linear, so we'll have exactly the same. You could also go through and work this all out. Like what is GF? Work it out, do the exact same steps. Like start the modulus is always positive, build up the function. But no harm in doing it just step by step here, getting the one for f and then plugging it in to get the one for g. All looks good. Hx is equal to k times x. K is a constant. Given that they have no solutions when this thing equals f, find the range of values for k. Okay, on these, the easiest thing to do is to draw it. We have f drawn, and we're told that h is just kx, so it must go through the origin. It's just a different, what gradient are we at? We need to hit it never. No solutions. But what that really means, we want to find one solution. You want to find the barrier between 0 and 2. So we must go through the origin, and we need to hit the curve, basically. So if we start at the origin, and I go this way, we will hit that curve there. I will just draw this a bit longer. So that's going to be one of them. And you can imagine, if I draw this again, everywhere on this way, I'm hitting it, aren't I? Hitting it, all the way. I'm still going to hit it over here. This line does keep going. When will I stop hitting it? Is when I'm parallel. Because you think, if I get, say, the slightest gradient just next to it, I will still hit it eventually. So I need to be exactly parallel with that line coming in to not hit it. So you can think this one, what's the biggest value of these? This is actually the steepest gradient. I know this is steeper, but it's negative in it. So this is like the biggest value. So this is, say, let's k max. This one is k min. So let's work both of them out. This one must just match the gradient. Like this is the same gradient. It had the gradient of -4, so k min is -4. The point at the bottom, when it hits there, we can use that to work out the gradient. It is at 3 and -5. So this is the point 3 -5. You get the 3 because it's x minus 3 in the modulus, and then -5, you can get that from this f bit if you want, or just in there, -5. So the gradient there, -5 on 3. So what do we need for the range of values for k? We have to have that k is less than the biggest one there, -5 on 3, and bigger than the -4 on the other side. So easier with the graphs, easier to draw it, I think, for these questions than actually just trying to do it with algebra. You have to be a bit tricky about like, oh, this hits, it's always going to hit that line every single time, but you need to have it only be hitting it like in the point when this line exists. So it's a bit harder to do than just think about, oh, let's just draw the graph and work out what gradient that line is. Sometimes it's not so easy. Let's do it that way around, but this way is generally going to work 95% of the time. Let's keep going to number 13. What have we got? It's given that for all values of k, where k is between 0 and 1, sine nx equals k has exactly 6 solutions in this interval. Choose the value of n. It's only 1 mark. So the reason they have to do this bit is basically saying that we don't hit the top. If you think about the shape of sine as I draw it, we're going to go up, down, back up again. Where does that top happen? Exactly at 1. So if k was equal to 1, it would only have 1 solution. Anything underneath that is going to have 2 solutions. 2, 2, 2. The 0 as well, they don't like too much because it's hard to think about like this one and this one and like not this one. So I think that's just to make your life a bit easier. And it might be as well, yeah, squared down here to say not at the bottom. So yeah, the 0 is actually not too important for this question, but it will be for that one. But the 1 is very important here to make sure we do cross this line in 2 different places. So that happens every full cycle. We get 2, but we need to have 6. So we need 3 full cycles. N refers to how many full cycles you have every 2 pi. So n must be 3. Just double checking that. Every full cycle you get 2 solutions. We need 6, so we must do 3 full cycles. So now, number of solutions in this equation between 0 and 5 pi. So I'm going to guess n is the same thing. So we know every 2 pi we're getting 3 solutions. We're getting 2 solutions, but we've squared it. So what actually really happens is it's a similar shape graph. It's a bit steeper and pointier, but it goes up, comes down, and then goes straight back up again and does a little double lump. So every 2 pi, we get uno, dos, tres, cuatro solutions. So every 2 pi will be 4. How many 2 pi's do we have? I have 2.5 2 pi's. So 5 pi is 2.5 times by 2 pi. Each 2 pi gets me 4. So it's going to be 2.5 times 4, which is going to be 10 altogether. Looks good to me. These are quite fiddly, only little ones. Sometimes it's easy to draw it, understand what's going on, or just actually try and just find it. Do you know what I mean? Just set them up and see how it's going to work. You know, n is 3, just solve it, see what happens. Because k is any number, it should be the same. You can just pick like a half, make it nice. Should work fine. Looks good. Let's keep going to number 14. What have we got here? Some vector stuff. So trapeziums, AD is parallel to BC, blah, blah, blah. They tell us lots of bits about where things are. Show you that K is 5. Okay, so what have they actually told us? A to B, we have that line. So the way I do it, I'm always going to colour in bits I've got to start with. B to C, it's over there, this line. D to B, going that way. So show that K is equal to 5. D to B. Can I move around these shapes? No, I can't really go anywhere on them, can I? But what I do know is that these are parallel on the top and the bottom. So where I have B to C, I know B to C is parallel to AD. How can I work out AD? Well, AD is the same as going from D to B, B to A. So D to B plus B to A. So we still have those bits. Let's actually work out what that is. So B to C, what do we have? 15 and minus 5. Why they do the A's and B's, I do not know. Vectors are always going to be nice to deal with as columns or rows. D to B, we have that it's going to be minus 4 and a K. And we have the B to A is minus 2 minus 3. But they should still say parallel. But what we can do with the parallel nature of it, that's the same as like proportionality stuff. We can replace parallel with equals K. So the right hand side is going to be equal to K lots of this thing. Maybe not K because that's a K, but we can add just some scale factor. Say alpha, lots of it. So we now have simultaneous equations. The top row, well, let's work that out quickly. So minus 4 minus 2 is minus 6, and then we've got K minus 3. These lots of alpha equals 15 minus 5. So the top row solves for alpha. 15 on minus 6. So it's going to be minus 2.5. And then using the second row then, we're going to have that minus 5 over 2, lots of K minus 3 equals minus 5. Those minus 5s will cancel. K minus 3 is equal to 2. K equals 5. And I think that was what they wanted. Yeah, lovely. So you can do this. Maybe what you want to do is write down that like A is equal to 1, 0 and B is equal to 0, 1. That's fine. There's no reason why you have to have your 2 dimensions in your axis be perpendicular. As long as they're not parallel, you're fine. And you can see A and B, I assume they're not parallel in this situation. Otherwise, like, they'd have broken the question, not you. So this is looking good. Given that also point N lies on BC, such that Bn to NC is 1 to 4. So let's get rid of these bits now. So Bn to NC is 1 to 4. So I need to split this into 5 parts. 1, 2, 3, 4. Doesn't have to be so perfect, do you know what I mean? But what we have then is like 1, 2, 3, 4, and a 1. Is that the right way around? B to N, another 1, and then 1, 2, 3, 4. So N is there. AN intersects BD at X. So we can draw that along here as well. And we know then this is point X. Find the ratio of BX to XD. So how do we split this up? So the way we're always going to want to do that is the X is the kind of unknown point. We know where N is. They told us the ratios about N's. So what we're going to do is take our X and we're going to find 2 different ways to get there. And you can see x has 2 lines on it. It's got this black line, b to d, and also the blue line, a to n. So we're going to start from one point. Where we start is kind of up to us. I don't think it makes a huge difference. You can see like we have BD, or DB, I mean BD, is on that line. It's already there. So I might just start with B. That might be my starting point. So B to D is the reverse of that. We got the K was 5, wasn't it? Yeah. So this is going to be 4 minus 5. So that's good. That's B to D. So what we can say about B to X then, it's somewhere along that journey. It's again parallel. So it's some scale factor of the longer journey. What scale factor? We don't know. Let's just call it mu. So it's mu lots of 4 minus 5. So that's one way to go from B to X. We could also get there going from B to A and then A to X. Do we have an AN? No, but we'll work that out eventually. So that's one bit. That's one direction. The other way then, B to X again. But we're going to go via A. So B to A plus A to X. B to A we know. A to X, what is that? We don't know. But A to N we can figure out. And we can say it's just some scale factor of A to N. I've used mu, so use lambda here. And then A to N, we can work that out as it's A to B plus a fifth of B to C. And now just go and work all those bits out. So what was B to A? That's going to be minus of this, so that's going to be minus 2, minus 3, if I can do math. Minus 2, minus 3, plus lambda, lots of A to B, which is 2, 3, plus a fifth of B to C. So a fifth of this. So 3 minus 1. Inside that big bracket, what do we have? 2 and a 3 makes a 5. 3 and a minus 1 makes a 2, and that's all times by lambda. So that is our expression that we have. I'm going to just move these ever so slightly so they're not on the diagram. But this is our new expression for B to X. So what we have is 2. We have 2 expressions to get there. I will write this one actually as like this is 5 lambda minus 2, 2 lambda minus 3. But they're both ways to get from B to X. So they must be exactly the same. So we have simultaneous equations again. Using the top row, we're going to have that 5 lambda minus 2 equals 4 mu. And the bottom row, 2 lambda minus 3 is equal to minus 5 mu. And then however you want to solve these, I'm going to times them to make 10 lambdas. I think it's probably the nicest way. Actually, no, let's make 20. So top row times 5, 25 lambda minus 10 equals 25 mu. And then for the bottom row, minus 25 mu, it's going to be times that by 4. So we have 8 lambda minus a 12. Let's add these up. 33 lambda is equal to 22. Lambda is 2 on 3. Did we need lambda or did we need mu? I should have thought about that before we solved it. We want to work out bxxd. So we want to go how far along this way. So we actually want mu. Mu is the answer we want. But we can then plug these back in to solve for mu. Let's think about the top row, say. So 5 times 2/3 is 10/3. Take away 2. That's going to leave you with 4/3. And that is equal to 4 mu. So mu is 1/3. So what we have then, if we look at this line, this is 1/3 of the whole thing. So this is 1/3. This is 2/3. So the ratio must be 1 to 2. Just make sure it's not 2 to 1. Yeah, bx is the smaller side. Bx was first, that's the smaller side. Yeah, that all looks good to me. And again, such a nice number, 1 to 2 coming out like this. It's a good sign. It doesn't necessarily mean you're correct, but if I'm getting something out that's horrible, it's probably not good. Probably not correct. Let's keep going. Number 15. Number 15's got some weird drawing of something going on. Let's get to the part of the curve with this thing. Curve intersects at -1 and 1. Minimum turning points P and Q. Use calculus, find the exact coordinates of P. Okay, this is a quotient, so we need the quotient rule. We have to have UV minus UV, that is on the outside, V squared on the bottom. This is quite involved. We've got like a chain rule down here, so I will do these individually. So let's just shove that up there. What is u? U is 1 minus x squared. What is u dash? Minus 2x. What is v? 1 plus x squared squared. What is v dash? Well, we need to have a 2 times that bracket times by the derivative of the bracket. So times by 2x. So that is 4x. 1 plus x squared. So let's stick all of that together. We're going to have the f dash of x is u dash v. So minus 2x. I'm just going to write bracket for a second because all the brackets are the same apart from like, unless I won't write them as a bracket obviously. So yeah, 2 bracket squared. Take away u dash v. No, take away uv dash, sorry. This thing times this thing. So we're going to have 4x, 1 minus x squared, and then that bracket. And then all over v squared. So that is the bracket to the power of 4. The reason I've done that, like the bracket's the same. If you want to, you can just like say that this equals, like we'll just call it a triangle or something, triangle squared. And then this is just triangle instead, like it's okay. So this is good. We can cancel off some of these triangles now. So let's do that. We're going to have a minus 2 triangle. Take away 4x, 1 minus x squared, over triangle cubed. And we really don't care about the bottom. We're trying to find like turning points, so we just care about the top. So if we set this equal to 0, we're effectively saying like 2 times that bracket, so minus 2 lots of 1 plus x squared. Take away 4x lots of 1 minus x squared equals 0. So let's expand all these brackets out. Minus 2, take away 2x squared, minus 4x plus 4x cubed equals 0. So yeah, we should get 3. You can double check, like we had 3 turning points in our diagram. We should have a quadratic popping out here. Should we have 0? I wonder if this should have all factors that are of x because we have this one at 0. What's gone wrong? We'll keep going. If I can spot it later on, we'll have another go. Let's rearrange this then, or that's already rearranged. We can divide by 2 though. 2x cubed minus x squared minus 2x minus 1 equals 0. Well, I guess it's 1. I'd guess 1 here looking at it, do you know what I mean? You got 2 minus 2 minus 1 minus 1. No, so it's not going to be 1 in this case. No, it's definitely not going to be 1, is it? This doesn't seem quite right. Like it doesn't seem like we want to be solving a quadratic, a cubic here for how much we've had to do already. And especially when we don't have a solution without seeing like that should be 0. I feel like this should have something different. So let me just track back through. We have u is 1 minus x squared. That's good. U dash minus 2. Okay, that's good. This looks good. When we differentiate it, the 2 comes down and we have that bracket, and then we have 2x. 2 times 2 is 4x, 1 plus x squared. That's good. Summing it all together, we're going to have u dash and v. So this and this. That's that. That's good. And then minus uv dash. uv dash minus. I've got the u. I've got the v dash. That looks good. On the bottom, v squared. V squared on the bottom. That looks good. We cancel out some bits. What we're going to have is, yeah, the triangles go. There was a square there, a single there, and a 4 there. So 1 went from each. That one's gone. That's dropped down. That's a cube. So we just have this bit. And that was 1 plus, wasn't it? Yeah. Minus 2. That's good. That's good. That's good. Not quite sure. But we'll use a cubic. Use the calculator to solve this cubic, see what it's given us. So we have 2x cubed minus x squared minus 2x minus 0. Sorry, minus 1 equals 0. And we get solutions that do not seem right. No, something's gone wrong here because we're getting imaginary solutions, and we should have obviously at least 2 real solutions, but only had 1. So let's scrap this off, start again. We'll just start the whole thing again, I think. I wonder if there's a way to like simplify it at all from here. I don't know if there is, or if we're just going to do quotient rule. Yeah, we will stick with quotient rule. So u 1 minus x squared, u dash minus 2x, v 1 plus, what I might do actually is expand that. Nah, let's not expand it. 1 plus x squared squared. V dash then 2 1 plus x squared single bracket times by 2x. Let's not do any of the triangle stuff. F dash of x equals 0, so it's the top row. Implies that we have u times u dash times by v. And we can then take away u times by, that's what I did, isn't it? I've done u dash v dash, take away u v dash. Yes, this should be u dash v. So I don't want half of those bits in there, do I? Yeah, that can go, that can go, that can go. That becomes a squared. There we go. That was a mistake. So we have, let's just double check, u dash v. This is then u, and we need v dash. Let's just duplicate that. Lovely. That thing equals 0. What we can do, again, one bracket there is gone. So this left-hand bit minus 2x times by 1, and then times by x squared, so minus 2x cubed. This bit, I've got 4x times this stuff, so it's minus 4x, but then positive 4x cubed equals 0. And now, yeah, we've got x's everywhere. How many x cubes do we have? I've got 4, take away 2 is 2. How many x's? Take away 2, take away 4, minus 6. Again, can factorize now. So x out the front, or 2x out the front. X squared minus 3. And now, yes, x is either 0 or positive or negative root 3. This is more what we're expecting. So in the exam, when you get things that pop up that the answers don't seem to match what they've given you, something's gone wrong. They will match what's appearing. They're not going to give you this where you've got 3 apparent turning points and then you solve it and you only have 1. You will have 3. And knowing that this one is pretty much at 0, this graph looks very symmetrical. Everything here is like, if I put in a minus, it's going to be the same. Do you mean? It gets squared straight away. The negative just goes, whether it's there or not. This is called an even function. It is completely symmetrical around this line. So I knew that it should have been plus or minus 3. So in the exam, you're going to make mistakes. You're going to get things wrong. You're going to just put down a v dash instead of a v. They're easy mistakes to make. You will never stop all of them. But what you can do is have ways that you can catch things at the end, which okay, something didn't match what's gone on here. So let's just start again. Something's gone wrong. Can I see it? No, let's start again because it is wrong. If you know something is wrong, don't carry on doing it because it's pointless. Do you know what I mean? You're not doing the right thing. Just go back, see what was wrong, start again, carry on going. So that's good. The exact coordinates of p, I need to then plug in the root 3. So in either case, x squared is just 3. So if I do that, what is f of plus or minus root 3? Should be the same. It's going to be 1 minus 3 over 1 plus 3 squared. So minus 2, it's not 2, minus 2 on 4 squared, so minus 8, 1 on 8. So our coordinates are either plus or minus root 3, but always with negative 1 on 8. It's not very good, 8. Let's try again. That'll do. Lovely. Now, use substitution. Show the integral of the thing we have is integral of 2 cos theta. So let's start off. X is tan theta. So x squared is tan squared. I never remember this way around. Cos squared plus sine squared is 1. So if we divide by cos squared, we're going to end up in a situation where we have 1 plus tan squared equals 1, equals sec squared. So we can rewrite the tan squared as sec squared minus 1. That is good. Same on the bottom. Do you mean 1 plus tan squared is just sec squared? So that's good. Sorry, it's sec squared, not tan squared. Now then, we also need the dx d theta. So differentiating tan, what do we get? We get sec squared theta. And let's look at our limits. If we have that tan is 1, like if tan's equal to 1, what do we have? It's going to be equal to pi on 4, and negative 1 is negative pi on 4. Negative 1 implies pi on 4, and positive 1 implies positive pi on 4. That's all good. So let's stick everything together then. We're going to have the integral of f. What was f? 1 minus x squared. Well, I know x squared is tan squared. So if I have, like, that's the same as sec squared. So 1 minus this stuff. So 1 take away all of that. I expand the brackets. I'm going to have 1 plus. I'm not trusting myself there. No, that is fine. Yeah. Yep, let's double check. I need 1 minus x squared. X squared is tan squared. So 1 minus tan squared. That does not equal sec squared, does it? No. 1 minus this thing. 1 minus that thing. 1 minus all of that. Expand that out. 2 minus x squared. So 2 minus x squared on the top. On the bottom, 1 plus x squared, all squared. 1 plus x squared, all squared. So sec to the 4. And then the dx we can replace with sec squared d theta. Sec squared d theta. Lots of bits will cancel. This is going to go. That becomes a 2. And then what we can see is we're going to have like 2 minus sec squared over sec squared. So the 2 over sec squared is just 2 cos squared theta. And then sec squared over sec squared is just 1. We haven't done the limits yet, but we did have like, yeah, minus pi on 4, pi on 4. Same on this one. And this is just then, it's in the book, and it's in the, not double angle, is it double angle? Yeah, double angle formula. So we can just use that from the book straight away. That this is just exactly what we wanted. Cos of 2 theta, d theta. Lovely. Next bit then, find that area. Actually do the stuff. Minus 1 and 1. We've already done that. That was fine. Yeah, it is exactly the same. Just careful they've not, like, it's not half of it or double of it or something like that. Do you mean it hasn't got it's got the same limits? So yeah, just perform this now. Haven't got much space here, so I will go to the next page. Let's copy that over. So integrating cos of 2 theta. We're going to have cos goes back to sine 2 theta, but it'll be a half of that. Pi on 4 minus pi on 4. So we've got a half of doubling pi on 4. Here's pi on 2. Same idea, but now negative. Pi's odd. Sine's odd. So that negative can come out and make a positive. So it's like we have the same, like sine of 2 pi, sine of pi on 2 on both. So it's 2 sine of 2 pi. Half of that is sine of pi on 2. So all 1 in the end. I think you can see that in there. It's 1 take away minus 1. It's 2, and then you have that 1. That all looks good. That's a very nice, again, that's such a nice simple number to get on these doing. Yeah, the last question on the paper, or is it the last? Should be one of the last. Yeah, last question on the paper gives you an answer of just 1. It's probably correct. Again, I will double check all these are fine. They look okay for me. If I've got something wrong, please whack it in the comments, and yeah, everyone else can see it then as well. Do you mean it's hard for me to check every single answer is correct without the mark schemes, but the methods should be right. That's the main thing we're focused on. The methods are correct. So lovely. Thanks very much for watching.